Take it and put it right back there.
Yeah,
Thank you.
okay.
Thank you very much.
My partners in crime are...
I'm Dr. Pamela Gay of Southern Illinois University, Edwardsville, and co-host of the Astronomy Cast podcast.
I'm Jerry Hester of Clemson University, just mere faculty. Mere faculty. Gotta give a big round of applause to Jerry. Jerry's the reason why this is happening. All this equipment is brought in his truck today, so... We also need to give a shout out to some of our assistants around the room. We have Kevin and Stephen and Mitch. Gentlemen, wave. And so I guess we're going to get started, right? So what are we starting with?
The tablecloth attempt of doom.
All right, tablecloth attempt of doom. I'll hand it to Pamela.
So way back about 400 years ago, there's this interesting notion that all objects tended towards non-motion. Human beings do that. You're all hitting the point in the con where a chair is a very good thing. Now, the idea of this Aristotelian thought was, if you start something rolling, it's going to stop. You start something dropping, well, it's going to hit the ground. And stop. Everything stops. And the truth is, everything actually stops if there's a force acted on it. So Galileo figured out, and this is before stopwatches, this is before machine equipment, this is before Excel, which is how every good science student does their laboratories. Back before all of that, he built a clock by creating what's called a water clock. It had a very small hole in the bottom, had a very large surface area, and drops of water came out. And the volume of water was how long it took for something to happen. And he did all of these experiments proving that it's actually only when there's a force acting on something that things stop. Now, the idea behind this is if I push something that way, it's going to go that way. If something's coming towards me and I push it that way, it's hopefully going to stop. Now, with these fine items that include an awesome juicy with the solar system on it, and a completely mediocre hotel bottle of wine. 3 little balls, there's a NASA bag, there's goggles I'm going to put on my face, because I'm going to do science. So I'm about to do a demonstration I haven't practiced at con, because I just came from Astronomy Cast's recording. So there's the great potential to do harm to fruit juice, which is really needed at this point in con, and wine, which is just really needed in general. Because what I'm going to do is I'm going to pull this pseudo tablecloth, otherwise known as a very slick surfaced trash bag, out from underneath these items. Now the only force acting on these items should be tablecloth going that way, but if I move it fast enough to overcome friction, then they'll stay put, and gravity is still acting, pulling them down. This is part of inertia. If I pull it fast enough and overcome friction, there's no force that direction. If I do it wrong, catastrophe to wine and juice and a NASA bag. Not practiced ahead of time. This is me testing if science works. Okay, can I have a countdown from 3? 3, 2, 1.
have a smaller surface area, and they stayed put. This did not. Now I'm going to give this to the person in the room closest to the age of 10 without going under. Do we have any 10-year-olds? Me.
Okay, so in case any of you are jealous of the 10-year-old, right now you're getting something passed out to everyone in the room. We have Kevin, Steve, and Mitch are passing out little cards to everyone, right? So just pass them down the road. They look like this. They say the Inertia Club on them, all right? Because this is a neat, fun, sort of audience participation way that you can take a demonstration like what Pamela just did and stick it in your pocket, right? You want to keep this as flat as you possibly can, right? So as soon as this little pile of cards comes down your row, take one. And you should also try to get out a coin of some kind. The more massive, the better. Like a quarter is best to start with, okay? You want to do that now.
And if you hang around afterwards, I'll try the tablecloth demo again and teach you how to do it.
Any extras left at the end of this row?
I think we're going to have a couple here.
Okay, pass those cards out, and we'll get cooking here on this next thing. Okay, so if you have your card, you have your Inertia Club card, hold it up. Hold up, let's go, hold them up, good. Okay, if you have your coin, hold it up in the other hand.
Just an announcement, everyone who has a coin, hold your coin. A great place to put these coins is in a donation bucket we will have here for people to help with science.
But don't necessarily give all your coins, because you have to have at least one to do this. Okay, so here's how it works, all right? Instead of a tablecloth, you have your card. Instead of dishes and wine glasses, you have your coin. Here's how it works. I have to kind of yell for this one, because I need both hands. Okay, so...
Donation boot.
So here's how it works. You take the card, put it on, I usually use 2 fingers, try 2 fingers. You put it on 2 fingers like this. Okay, now people in the front row, watch out, because it's coming at you, okay? Or I'll turn this way, okay? You put the coin on top like so, and then you try to remove the card without moving the coin, like so. Right? Give it a shot, go. Nope. Now, if you can do that, you can play this game with your friends, okay? If you can do that, try with a less massive coin. Try a nickel. Okay, here we go. Okay. If you can do that, what's next less massive? Penny. Try a penny. Okay, watch out. Watch for no. That's gravity. That demo's later. Okay, try a penny then. Try a penny then. Here we go. Okay. What's less massive than a penny? 9, right? So try dime next. Now, we run out of U.S. currency, but I'll tell you a couple other quick things you can do with this. If you get to the point where you're good with a dime and you can do this consistently, in Japanese yen is about half the mass of a dime. And a Czech Republic little tiny coin is about half the mass of Japanese yen. And here's like the ultimate in the Inertia Club awesomeness. If you can even get to the point where you can do that consistently, I challenge you to try it with a single grain of rice. Now, the demos that we just did here, this is where we're like pulling on things, right? Okay? So, what about if we do the opposite? What about if we push on something? Let me introduce you to my little friend. Jerry, this is a, what, 50, 55 pound anvil, roughly?
Something on that order.
Okay, so we got this really massive anvil up here, okay? Now, yeah. Now, if, in order to see this next part, you need to be able to see kind of this part of the stage, because what I'm going to do is I'm going to lay down, and Jerry's going to put this on my chest. And then he's going to hit it as hard as he can with this dead blow hammer back here. Hold up the hammer. Okay. Objects at rest have a tendency to remain at rest, right? I call this sacrificing myself for science. I have to take off my lab coat. Don't get excited. Okay, you can get excited. That's later.
I just heard someone ask, is this a magic trick? No, I can't lift that anvil. His stomach is stronger than I am.
That all depends on if he's still breathing.
Ready?
Yeah! Oh! Harder! Harder! Is that all you got, Jerry? Don't miss! Oh! One more time! Oh, once! Give him a Jerry!
Okay, now, we need to do a little bit of moving around on stage, so we're going to have kind of a neat little kind of semi-light show here for a few minutes. Steve, if you could get on the line, and I was going to say something.
Okay, so your TV has, most TVs, especially old TVs, if you get way too close, something your mother has told you never to do, you can actually tell that there's 3 different colored square bits side by side. A green one, a red one, and a yellow one. Blue one. Sorry, I lied. I listened to my mother. But when you look at your television, it has all these different colors. And this is from color mixing. And any of you who have played with paint know that by combining different colors, you can get all sorts of different things. So here we have a case of color mixing in action. So what you're seeing is each of these balls has within it, I guess that one is red, blue, and green, and the other one's red, blue, and green, LEDs that are flashing very rapidly. And if he holds them still, as he's doing with the one, you see the combination of all 3 colors adding together to get this weird purpley color. Now you start moving it, and you can see each of the colors separated, and you can also tell how fast it's blinking in a certain way.
Check this out. A little bit slower.
So now you can start to see the overlapping regions, to start to see how they're able to create so many different colors of the rainbow. Your eye is actually made up of a bunch of different cells that are each sensitive to just one range of that rainbow. So when you look at things, your eyeball is doing the exact opposite of what the television's doing. It's taking the whole distribution of colors. Go ahead, give a big shout out for Matt Lowry. So, from your television, it produces 3 colors that get blended. Your eye then samples those 3 colors in a different way, and we build full color pictures, 3 colors at a time. Biology's kind of awesome, and it's science too.
Okay, we're going to drift off a little bit into electricity for a few minutes. So, has anybody in here ever been shocked by a cord or something like that? It hurts, right? What sort of a potential and voltage is that? 120? 120 typically. So you figure that the higher the voltage, the more pain or things, right? No? Amps, the current, okay? So I have something here that called a Graaff Generator, and we're going to see how it works. On a good day, it gives about 400,000 to 500,000 volts.
How many amps?
If any of you ever visit Boston, the Boston Museum of Science has the world's largest Graaff Generator. They generate in-the-door lightning storms with complete lightning bolts. It's awesome, terrifying, and was originally used to try and split atoms. If you can't see, feel free to move around, especially small children.
Insert comments as necessary.
Bring the lights back up. Okay. Now, everybody's walked across the carpet and grabbed the doorknob, right? And gotten shocked. But that's not, you know, that sort of arcs about that much. Now, this one arcs about that much. So it's a little bit different, and if it shocks you, it does. So in a little while, we're going to call for some volunteers. Because I really don't like getting hurt. Now, you can do strange things with a Graaff, like, by the way, this is Harvey. Harvey looks worse than he is. He leads a rough life. But Harvey's really okay, and he's pretty well trained. And Harvey, up, down, Harvey, up, down, Harvey, up, down, Harvey, up, and down, Harvey. So he does well, right? And we can do... More power, Jerry. More power, Scotty.
The power of gravity, ladies and gentlemen.
Now, you can also do strange things with a Graaff that are sort of like, you get a arc like that. You turn the lights down again. Now, trust me, when you see it arc like that, it hurts.
How bad is it?
Now we need a volunteer. Somebody preferably with fairly long hair.
No product. No product.
They didn't put products on it. Okay, see, that doesn't work.
Stays down, right?
No guarantees.
Me too.
What I'm going to ask you to do, Ed, is I'm going to stand up here. Now, the most dangerous thing here is getting on the bucket and off the bucket. Okay?
You need a spotter, sir.
And what I'd like for you to do is then just lay your hand up here, gently. Okay? Now, what you don't want to do is a lot of people, they do that, and then they turn it on and they go, oh, my hand's supposed to be there, and they go that. You don't want to.
That's why I leave the cell phone.
That's probably a good thing. All right, so if you would, Ed.
To you will be fine.
How do you guys like your barbecue?
I'm looking for parts.
line in half.
What?
Cut the line in half.
Cut the line in half? Okay, let's cut the line right about here. Okay. Right there. Okay, no. Okay, what about now?
I'm hearing it discharging somewhere and I can't tell where.
It's over here!
Over there?
Coming out of the speaker.
Yeah.
There must be a mic. There must be a mic near one of the people.
Well, I think we're on the side we go.
Yep, we're on the side we go.
Okay.
So we can, I can prove that if I cause him pain, that the electricity is making it this far. I'm sorry, sir. Punch him!
Hey, Jerry, should we have them stand up here?
Well, we could. For a few of them anyway.
I think we should just move on.
Let's just move on. Yeah, we got other cool stuff.
So we showed you electricity moves through you.
You party the other
Volunteer, stay here. I want the volunteer to stay here.
Okay, we have laser pointers for our volunteers in order of the pay received due to closeness of the device.
Volunteers here.
Yeah, yeah. Let me turn back on.
Yeah, sorry.
I think your hair goes back.
One more time.
Okay, now, are you ready? Are you ready?
Shocking.
So we're about to show you a demo involving electricity, because electricity is fun. Now, I'm an astrophysicist, so we don't usually get to deal with electricity. We're dealing with a lot of light, a lot of gravity, relativity, cool stuff, but very little electricity. So these are the experts who are going to play with the demos that shock us. Now, with the Tesla coil, we have a beautiful old-fashioned example here. What's going to happen is electricity is going to come out of this giant, rather, looks like it's going to make Frankenstein power source. It's going to coil around this tube. This isn't carrying fluid. I know it looks like a water pipe from your house. It's carrying electricity. Now, inside of this is a big old mysterious looking device that if you took it apart, you'd find there's coils of wire inside of it. Now, this is going to do something called induction. What happens is, when electricity flows, it creates a magnetic field. And the magnetic field is created such that if current is flowing through my thumb, the magnetic field curls around my thumb. This is the type of thing that when you're learning physics makes you cry, because you have to remember what hand to use. And if you're writing with your right hand and try doing your homework using your left, you get the whole thing wrong. Now, yes, lefties rule with this one. Now, the thing is, the Earth has moving current inside of it. This is because we have really hot ionized material creating what's called a dynamo inside of our planet, and that's generating the Earth's magnetic field. Sun generates magnetic fields, there's magnetic fields anywhere.
And if you make a magnetic field change, that generates electricity. So if you create current, current creates magnetic field. Change magnetic field, create current. It's this wonderful cycle. Now we have this problem called we have a sun that does bad things occasionally. The Earth's sun has sunspots, which are places where the sun's magnetic field pokes through the surface of the sun and makes the sun look like it has a bad case of the freckles or acne, or pick whatever blotchiness you would like to pick. And all of these places where the magnetic field pulls out, occasionally these loops break, releasing high-energy particles that come streaming straight towards the Earth. And they interact with our Earth's magnetic field, make the Earth's magnetic field vibrate violently. A changing magnetic field creates electricity. Now the Earth is kind of covered in wires. Wires act the same way the wires running through that act. Now, when those wires experience that changing magnetic field, it changes the amount of electricity running through them. Now, if any of you have plugged in a hairdryer, turned on the microwave at an inopportune moment, you've blown the fuse in your house. When the sun turns on the Earth's magnetic field, it blows out the power grid in Quebec. This actually happened back in 2003. Many of you in the Northeast probably experienced it. I was trying to move cross-country that day, and when they can't take your credit card, they give you free ice cream because the freezer no longer works, and then smile sadly at you about gasoline. Now, he's about to do awesome things, so since he's set up now, I'm simply going to stand here and hold a mic so he doesn't have to be attached to a wire while holding electricity.
Okay, I'm just going to start with a handheld Tesla coil, and then we'll switch to this one. This is an old one that I found in my demo area and sort of rebuilt and put back together. These handheld ones, they operate on about 50,000 volts. But these things will deliver a very significant current. In fact, they will deliver a current that would be deadly under normal circumstances.
Deadly.
But we have the advantage. These sort of oscillate. So they oscillate very, very rapidly. And in fact, this one oscillates at about 1.5 million cycles per second. So it triggers that. Now when I turn it on, it's going to be really, really noisy and things like that. And we don't want to leave it on for very long because it generates lots and lots of ozone. That's good. But just to demonstrate some of the effects of a Tesla coil, we have here some spectrum tubes.
These are the same things the neon lights you see at bars and restaurants are made of. They're just filled with different gases. And each gas, each atom, glows with its own specific sets of colors. So here what you're seeing is at various points mercury, that's the blue on the left. I believe that's hydrogen. Neon, sorry, trying to look at colors. Argon. Hydrogen.
And oxygen.
And that one's oxygen. So you can see each of the different characteristic colors. Now that oxygen one, the green on the right.
One of the fluorescent tubes.
Can someone hand us a fluorescent tube you can vaguely see in the front of the room? So when you see green planetary nebulas, green objects in space, what you're seeing is things rich in oxygen. And do with the flash, that flash just isn't going to work, but feel free to come forward to the front. So fluorescent light, that's just excited atoms.
They're excited about science.
They're excited about science!
And that's how we know what the stars are made of. Because
right.
We can examine the light.
Like a lightsaber.
Okay, this Tesla coil is going to be operating at about 500,000 volts. I started with this old neon sign transformer at 15,000 volts, and then it feeds into this, and finally gets to this thing here that has many thousands of windings, and it's called a step-up transformer. And so it takes this 15,000 volts and steps it up many times to a much higher voltage.
This is basically like, well, you know those gray cylinders at the top of the power lines go, right? That's basically what this is, except it's exposed. Jerry Hester.
We need everyone to move back.
Well, if you're seating, you're okay, but people in front need to move out of the way.
No one sitting on the floor. My friendly person, even larger people need to. If you can be beyond the edge of the stage in both directions.
Okay, so I'm going to get out of the way and talk for a few moments while we're setting up here. And I'll pass it to Pamela in just a moment. We're going to finish, because we only have about 15 minutes, so we're going to finish with a couple of demonstrations of the physics of pressure. We're going to finish with a couple of demonstrations of pressure. And these demonstrations are a little dangerous. And which is why I'm going to be doing them. Crazy, yes.
Mad science!
Awesome. Okay, and as a way of giving you an idea of why it is that I'm going to hopefully walk away from all of this uninjured, Pamela has a couple of things to say, a little demonstration to show you over here on the podium. Okay, so Pamela, take it away with that.
And I'm going to ask our minions to break down this table so people on this side of the room can see better.
You are the best audience ever. Okay, so here at Con, you've seen a variety of footwear. There are, and this is my footwear, so even scientists go for stilettos now and then. So you've seen heels like this. You've seen heels like this. And it's Sunday night. You've seen lack of heels as well. And now you're seeing a PhD scientist giving a talk in bare feet. So, pressure is force over area. So if I step into the elevator, and I would never do this, so if a random con person, big person, bigger than me, 100 kilograms, because that's a round number, is wearing these shoes, and steps on you, all weight in one foot on the heel. I actually, the first time I taught this in class, I gave this number. It wasn't written down on a little tiny piece of paper like this at the time, but the amount of pressure coming from this is 39,200,000 newtons per square meter. One of my engineers, who was sitting in the back of the room, I'm sure doing something he shouldn't on his computer connected to the internet, goes, "Could that destroy a brain?" So, imagine, ignore the physicist behind me. So imagine for some reason you are asleep on the floor in the lobby of the Marriott, insane 100-kilogram person wearing these shoes steps all force in one foot on the stiletto on your head, that would go through your skull. Yeah. Now, these boots are a little bit safer. You step on someone with these heels, it's significantly bigger. That is about half a centimeter per side. This is about 2 centimeters by 3 centimeters. Ignore the physicists behind me. If you were to be stepped on with this, it probably wouldn't break your skull as long as you were lined up correctly. In that case, the pressure is about 16 times less. It's 1,633,000 newtons per square meter. That sucks. Now, luckily, at this point in con, all of the droopy, tired, exhausted people who can't walk real well have decided to carry the heels. And this makes your life much safer. Because we're that person to put all their weight down on you, wearing the flip-flop instead. So we have flip-flop versus stiletto. The amount of pressure coming from the flip-flop is 78,400 newtons per square meter. That is a factor of 500 less. 500 less. Stiletto versus flip-flop. More people should wear flip-flops to save the planet from high-pressure situations.
Shoe science.
Okay, so what I've been doing up here is I've been crushing up some glass. So for those of you who saw me walking around the con the first couple of days with this big bag slung over my shoulder and picking up random beer bottles, that's where they are now.
Your contribution to science!
Science! So I guess the lesson here is drink more beer. Now, what I'm going to do, as I mentioned a few moments ago, is I'm going to sacrifice myself for science by walking on this broken glass.
Infection!
It's okay, we're in Atlanta, the CDC's closed.
Beer bottles, they're sterilized.
Now, the trick to this is, it's a biology experiment. The trick to this is that if you're going to walk on broken glass shards like this, first of all, kids, don't try this at home. Okay. These are sharp. You can get cut, and actually, when Jerry and I were working earlier breaking it up, we both cut ourselves. I got a cut on my thumb, he got a cut on his hand. So this really is really sharp stuff. And so what we're going to do is we're going to spread this out, and I'm going to show you exactly how this works.
No, he claimed he was wandering around collecting beer bottles, but he was really up really late last night. Nearly enough. Now, do we have a volunteer for this one?
This is where I remind you, I'm an astrophysicist and will not be participating in this experiment. Be careful, there's broken glass right there.
Okay, so...
Yes.
Yeah.
We're recording.
Because it's fun. Okay, now, I've done this this demonstration about 100 times, and every time, right when I get to this point, I think, what do you want to be thinking? Because I'm about ready to step on broken glass. But you know, physics works for everybody. And the way this works is if you step on the glass and you avoid stepping on, say, pieces like this, which can roll under your foot and cause your foot to move side to side this way, causing a nice slicing action. Yeah. If you step on them straight down, flat-footed, you distribute your weight over many, many points. And if you distribute your weight over enough points, then what happens is the pressure at any one point isn't enough to penetrate the skin and cause a cut or a puncture. So let's see how this works.
Does anyone know if 911 works in here?
No signal.
There is glass completely under his foot. That side-to-side motion is to make sure there's nothing that will roll under his foot. He is standing on glass. And my heart has just gone faster than it has gone ever before. And I trust physics. And there is no blood, and his feet are a little bit dirty, but awesome.
Now, we're not done. We have one more demonstration to do, and we're saved the best for last. So, what I want to do is I want to direct everybody's attention over to the screen, because in a moment we're going to play a little video as a way of introducing us. This also gives us a chance to kind of clean things up here a bit.
While we're getting the video started, we have one more NASA Graaff bag to give away. And because I'm a scientist, I'm used to working in logarithms. So having given away a bag to the person closest in age, but without going under to the age of 10, we are now going to give a giveaway bag to the person closest to the age of 100 without going over. Do we have anyone who's 100? Okay, do we have anyone over 90? Over 80? Over 70? I love the fact that this room is young. Anyone over 60? We have the winner! So if you will now turn your attention to the video and we can have the lights down again, we shall watch the humiliation of Matt Lowry. And I have to say, he's a high school teacher. We need more teachers as awesome as him.
Science is heating up. Apparently.
18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. safe science.
Okay, yeah, that hurt. Yeah. That was a demonstration of this demo right here. This is called the bed of nails. And in case you couldn't see the video, I was laying on a bed of nails. I had another one put on top, that was a cinder block. And the idea is somebody comes along with a sledgehammer and breaks the cinder block to smithereens. Now, two things went wrong. I think the second was obvious. But the first one is when my partner on the video, Jessica, when she hit the cinder block, it didn't break, which is really, really bad. Because you want the block to break for multiple reasons. First of all, one reason I don't get stabbed to death is because I'm touching a lot of sharp points. This is just like what we talked about with the broken glass. Okay. The other reason is when she's wielding the hammer and she's hitting the cinder blocks are very massive, right? Just like the Handheld. But the reason why you need the block to break is because if the block doesn't break, all the kinetic energy behind the hammer goes straight where? Me. Yeah, right into me. And it feels like you get hit in the stomach with a sledgehammer. So when the block breaks, a lot of the kinetic energy just basically goes into breaking the block and all those pieces fly off. Okay? And with that, ladies and gentlemen, our final demonstration of the evening is the infamous bed of nails. Don't try this at home.
And I'd like to point out, since this is a pressure over area, you can't do it with people who have pointy bits. So women in the audience, you never have to lie on the bed of nails and have cinder blocks broken on your less than flat surface.
Volunteers. I must be nuts.
So the reason that Matt's getting help is to make sure that he goes down fairly flat so that his weight starts out spread across a number of nails. If this was a single nail, he'd be impaling himself right now. We like Matt, we don't want that. So he's making sure that he doesn't accidentally put weight down on just one nail on any particular part of his body. The arms are a particularly hard one because the spacing of the nails makes it so that you only have two rows of nails touching your upper arms.
Please don't forget all the free beer I've provided over the years to you people. you want to rate more than 5 stars, send an email to dragoncon@dragoncon.org and tell them, yes, we want more of this. Science!
Make sure they're behind you.
I went to get food and I thought it would only take a few minutes. Apparently there's a lot of people here for things to go in science. I think we need some bigger I think Labor Day weekend they should stop here and see